This is example 9-3, filling of a tank. So we have this cylindrical tank here, and we have that contains, or is supposed to contain, crude oil. And we are now filling this tank through this horizontal pipe down here, given what the diameter of the pipe is. And we are asked how long it's going to take to fill this tank up to 2 meters. And we're given the constraint that the flow is supposed to be laminar in our infill pipe here, right? So that means if we want to have the shortest time while it's laminar, means the fastest velocity while it's still laminar, right? Because the fastest velocity is going to give us the fastest volumetric flow rate, which is going to make it fill fastest. So we can say shortest time means fastest flow. That is still laminar. Right, so we can use our flow in a pipe equations for that, right? So, but if we want to be laminar, right, we know that what our Reynolds number has to be, right? Our Reynolds number in a pipe has to be less than 2,300 for it to be laminar. So we can say RE is equal to rho times V times D through a pipe here, like a P for a pipe, because we also have the diameter of the tank, divided by mu. Solve that for our velocity, then we get the velocity is going to be mu times our maximum Reynolds number divided by rho times d pipe. All right, so that's our velocity. Now, if we want to fill this tank, right, we want to have this tank full, so we can figure out the volume of the tank is. We can say volume of tank, right, that's a capital V. And of course, in our case, because we have a flow coming in, we can say the amount of fluid or the amount of oil in this tank is the flow rate times time. What's the flow rate? Well, the flow rate is the average velocity times the area of my little pipe times time. And so, of course, we can find the area. That's just pi over 4 times d pipe squared times t. Right, that would be our volume. So we can now solve this for t, because that's what we're looking for. So we can say that means that t is equal to, well, we have to multiply by 4, right? So we'd have 4 times v divided by pi times dp squared times our velocity right there. And be careful with the capital V up here and the lowercase v there. All right, so we want to find this time when the tank is at 2 meters depth, right? So we can say that would be 4 times the volume of our tank is going to be the area, so pi over 4 times d of the tank, so let's say dt squared times the height, which is h, divided by pi times dp squared. And then the velocity we figured up here was mu times the Reynolds number divided by rho times d of the pipe. And with that, I think we have only knowns in here, so we can start plugging in numbers. Right, we can say on top, actually we can simplify that a little bit before we do that. If we simplify, right, we can cancel those two 4s out. This and this. We can cancel one of these. So that should leave us with top here, oh, we can cancel a pi as well. So that leaves us then with, on the top, we'll have dt times h. dt times h, dt squared times h. And then from down here, we're left with a rho, so let's put that up there. Divided by, this is all canceled out. That's dp times mu times our maximum allowable Reynolds number. Okay, now we can plug that in. That's nice and easy. The tank had a diameter of 2 meters. So 2 meters squared. The height is another 2 meters. The density of the oil is supposed to be, it's not given to us, but we can look it up, at 20 degrees C, is 880 kilograms per cubic meter. Divided now, the diameter of the pipe was 60 millimeters. So that is 0.06 meters. The viscosity we can look up as well. That is 30.2 times 10 to the minus 3 Newton seconds per meter squared. And then what we're left with the Reynolds number. We said the maximum allowable would be 2,300. All right, with that, let's plug the numbers in, and we get 1,689.22 seconds. Right, if we divide that by 60, right, then we get 28.15 minutes. That's how long it takes us. Right, it would take 28 minutes to fill the tank up to the level that we want at 2 meters, and still have laminar flow in the pipe. All right, so that was the first question. The second question is, what is the pressure gradient? Well, to get the pressure gradient, we can say in a horizontal pipe, we know that the velocity is given as the d, so as in our case, d of the pipe squared over 32 mu times delta P over L. Don't have to worry about the delta H because we're at a horizontal pipe. And we also figured out that V is equal to mu times our maximum RE divided by mu rho times D pipe. So we can solve that for dP dL, or delta P over L, is then equal to, well, what do we get? We have to multiply by 32 mu. So we'll get 32 times mu squared, because we already have a mu there, times the Reynolds number, divided by rho, and then we divide by that d pipe squared, so we get d pipe to the third power. And we can plug that in, and that gives us 32 times 30.2 times 10 to the minus 3 minus 3 Newton seconds per meter squared, all of that squared, times RE, so 2,300, divided by the density was 880 kilograms per cubic meters, times 0.06 meter raised to the third power, which gives me 353.147 pascals per meter. So that would be our, let's make that delta there look more like a delta instead of a D. All right, so our pressure gradient would have to be this to fill the tank that we have in 28.15 minutes using the fastest allowable flow while it's still laminar.